Hi everyone, welcome back. So in the last video we used Python to plot the chaotic dynamics of the dimensionless discrete logistic equation for certain values of r. So like for some values of r you had your nice cycles, but then we found that when r is say 3.8, your points went all over the place and didn't seem to have any sort of nice rhyme or pattern. Let's try to formalize parts of this idea. And the first thing we're going to do is we're going to define something called sensitive dependence. So this is definition 2.7. It's just basically going to capture the idea that even if you start close together, you don't necessarily stay close together when you have when the function is chaotic in some way. So we're going to have some function f from I to I. Well, then the map f has sensitive dependence. On the initial condition. So our starting point x naught. If there exists some delta greater than 0 such that for any epsilon greater than 0 there exists some y naught in our interval and a natural number k such that x naught minus y naught is the absolute value that's less than epsilon, so the 2 points start out close together. And after repeatedly applying f to k times to each of x naught and y naught, the distance between the two of them after applying fk times is greater than delta. So intuitively, basically what we're saying is that there is some distance delta such that no matter how close you get to x naught starting off, after some number of steps, k, the two trajectories diverge, even if you started super close to each other. So let's try to measure the sensitivity. So basically the sensitive dependence is just saying, oh, well, even if you start close together, you eventually get far apart. We can also measure how quickly things get far apart. So let's try to do that. So we're going to, for a given initial condition, so for a given initial condition x naught, let's define this distance, delta of epsilon comma t, to be equal to f to the t of x naught plus epsilon minus f to the t of x naught. Okay, so what are we doing here? We're just saying that if we start at some point x naught and we go some distance epsilon away, how far away is are the respective trajectories of x naught and x naught plus epsilon after some time t, so after t time steps? Well, let's solve this for a simple problem. So let's suppose that we have a very simple difference equation. X sub t plus 1 is equal to 2x sub t as a simple example. And let's look at it around x naught equal to 0. Well, one, we know that delta epsilon comma t is going to be equal to, well, let's see, we're repeatedly multiplying 2 each time we do stuff, and so we start off with 2 to the t times x naught plus epsilon, since that was our original starting point, minus, well, 2 to the t times x naught, which is just equal to 2 to the t times epsilon, which is equal to, we can rewrite this, and this is maybe a little bit odd that we're going to rewrite it this way, but it'll make our next definition make more sense. Epsilon times e to the t times the natural log of 2. And so this is the dependence on epsilon and t for this very simple case where the trajectory is at the point 0, which stays at 0, and the trajectory at the point x naught plus epsilon, which diverges away exponentially quickly as t goes to infinity. This is a very simple example, and it sort of captures the behavior that we want to be measuring. So what we want is that delta of epsilon comma t should have linear dependence. Linear dependence on the starting distance, linear dependence on epsilon, and it should have exponential dependence on the number of steps. Should have exponential dependence on t. So, plus, we can define something, or we can consider defining defining something called the Lyapunov exponent. Actually, let me put this in blue. Lyapunov exponent. Lambda of x naught by epsilon e to the t lambda of x naught is about equal. So this isn't actually a definition because we haven't quite made this formal. But we're going to say that epsilon e to the t times lambda of x naught, where in the previous case that was just the natural log of 2. In this case, we don't know what it is yet, since we're talking about an arbitrary difference equation. It's going to be equal to f of t applied to x naught plus epsilon minus f of t x naught, where epsilon is small and t is large. And of course, we need to formalize what exactly we mean by this. So we're going to let epsilon, let's say, so we're going to let epsilon go to 0. That's a pretty small value of epsilon. So if we do that, we get that e to the, so then we get epsilon, let's divide both sides by epsilon. So then e to the t lambda of x naught is about equal to the limit as epsilon goes to 0 of, well, if we divide everything by epsilon, then we know that epsilon is greater than 0. So this is f to the t over x naught, or of x naught plus epsilon minus f to the t of x naught divided by epsilon. But now this here is just equal to a derivative. You notice that this is precisely just the absolute value of d dx of f to the t of x naught. Which implies that lambda of x naught is equal to 1 over t times the natural logarithm. I didn't need that limit there anymore. Times the natural logarithm of d dt of f to the t of x naught, which is equal to 1 over t times the natural logarithm. Well, if you apply the derivative, as we saw last time when we were talking about using the first derivative test with respect to the repeated function composition, this is just equal to the natural logarithm of f prime of x naught times f prime of x1 times all the way through f prime of xt minus 1. And so we saw this when we were looking at the m cycles and trying to apply the first derivative test to one of them. But the first derivative doesn't actually depend on the fact that it is a cycle. And so this is equal to 1 over t times the sum from k equals 0 to t minus 1 of natural log of the absolute value of f prime of xk. Okay, but we still have a t dependence, so we're going to, but still have t dependence. So we're going to let t go to infinity, since infinity is a very big number, so we're just going to take lap limit as well. So then we can say lambda of x naught is equal to the limit as t goes to infinity of 1 over t times this sum from k equals 0 to t minus 1 of natural log of the absolute value of f prime of xk. Okay, and that leads us to an actual definition. So there we were sort of giving a heuristic description of the sort of properties that we want in this Lyapunov exponent. And here, now we can actually just define it as this double limit. Well, as a limit as t goes to infinity and as epsilon goes to 0, which then gives us the derivative. So this is definition 2.8. the Lyapunov exponent. And sometimes I might spell it with a y, since the English transliteration allows you to use either an I or a y there. The Lyapunov exponent, let's go back, at some point x naught of a difference equation x sub t plus 1 is equal to f of x sub t is, well, this thing. So we've already defined it. Lambda of x naught is equal to the limit as t goes to infinity of 1 over t times the sum from k equals 0 to t minus 1 of the natural log of f prime of xk. And it turns out that sometimes this will be independent of x naught. So if lambda of x naught is independent of x naught, well, then we can denote it by, then we don't need to drop the x naught. It's denoted just by a lambda and referred to as the Lyapunov exponent of f. And there exists sensitive dependence on initial conditions. If lambda of x naught is greater than 0 for all initial conditions in the domain. And so now intuitively what's happening is that when the Lyapunov exponent is greater than 0, you have your exponential causes things to separate out really, really quickly. No matter where you start out. So if you start out at a place and you start out even just a little bit far away from it, their trajectories diverge over time. And just as an aside, this is actually going to be quite useful, but we can verify. So this is something that I think I might have one you do in one of your exercises. I'm not sure yet. But so we can verify that all stable equilibria have negative Lyapunov exponents, and all unstable equilibria have positive Lyapunov exponents. Okay, and so we can sort of see that in our example up here, where what was a Lyapunov exponent here? Well, the Lyapunov exponent there was just natural log of 2. And of course, the natural log of 2 is positive. So, okay, continuing on. In practice, it turns out that this is actually quite hard often to compute. So, in practice, Lyapunov exponents, Lyapunov exponents, exponents of for non-equilibria. So we can compute them for equilibria, which we'll show you in the next video. But for non-equilibria, they're harder to compute. So we often just approximate them. Via computer. So the first thing to note is that for fixed j, lambda of x naught is equal to lambda of xj. Because we're taking a limit as t goes, of xj. Because we're taking a limit as t goes to infinity, and so it doesn't actually matter if we start at x naught or if we start at xj, because as t goes to infinity, it all falls out. So we can say that something like lambda of x naught is approximately equal to just 1 over n as for the sum over k equal j to k equal j plus n minus 1 times the natural log of the first derivative of each of those points. And so you can just have a computer run this for 1,000 points or some number of points, and then you take that as an approximation of the Lyapunov exponent. And another aside is we've only defined these things for a single first-order equation, but we can also generalize this to a system of first-order equations. So we can also generalize to system of first-order equations. X sub t plus 1 is equal to f of x of t, where these are, this is a system of equations instead, and so these are vectors. And we can do this by using the Jacobian matrix, which we'll cover a little bit more in the upcoming lectures. The Jacobian matrix J of x of t, but it's something that is quite useful, and you should have seen this in your multivariable calculus class. And then we want to look at the spectral radius, looking at the spectral radius rho. And in that case, we have that the Lyapunov exponent lambda of x naught of some value is equal to the limit as t goes to infinity of the natural log of rho times this product for k equals 0 to t minus 1 of each of our Jacobian matrices. Okay, you'll note that we haven't actually taken we haven't actually turned the logarithm into a summation just because we no longer, and we do that outside of the product. But it still is effectively the same sort of thing, but just because it's harder to take to separate out these logarithms when the product is of matrices as opposed to of scalars. And so this turns out to be pretty hard to compute, though it is still something you can define. And turns out that if lambda of x naught is greater than 0, then the solution to the system exhibits sensitive dependence on the initial condition x naught. And in general, if the solution is not asymptotically periodic, so if it doesn't eventually limit to a cycle, and no Lyapunov exponent is exactly 0, then the solution is chaotic. So we're mostly going to, this is chaotic. We're mostly going to focus on the case where we're only talking about a single equation, and we're not going to talk as much about systems of equations, but it's important for you to know that these ideas of chaos really do also apply for systems of equations and higher dimensions. Often when you see examples of chaos in nature, they will be these more complicated systems. Well, thank you very much. And that will be our first video on this topic. And in the next video, we'll go back and give a couple examples of this just to clarify a couple things about these exponents.